Hello and welcome. In this mixing problem involving two closed subsystems, we have hydrogen in one tank on the left tank and CO2 on the right tank. We allow these two tanks, the two gases to mix and reach equilibrium, at the end of which both tanks will have hydrogen and CO2. We are asked to find the final temperature, final pressure, and the entropy generation during this mixing process. Of course, the condition of each, there are three states involved. State 1 is the subsystem consisting of hydrogen. State 2 is the beginning state of the subsystem B. And finally, we have a single system of the mixture, state 3. So sufficient information is supplied for each state except for the last state, final temperature and final pressures are not known, but the tanks are insulated, so there is no heat transfer. So the energy equation will hopefully produce the missing link. Okay, so let's go and launch a suitable test step. Of course, it's a closed process. We follow the closed branch, generic branch, and it's a mixing process. That is, mixing is complete, we reach equilibrium, as opposed to semi-mixing, where we close the valve prematurely. So we go to the mixing process, and the problem states that we should assume constant specific heat. So therefore, PG plus PG model will be the best model because we have a binary mixture in this case. So first, the two fluids that we have are hydrogen and CO2. That's how the binary mixture is made of. Fluid A and B, it happens to be my subsystem, which is state 1, is purely hydrogen. So therefore, how do you make pure hydrogen? This is X of A, mass fraction of fluid A. You can either assign mole or mass fraction. Mass fraction of fluid A, if it is 1, which means we have pure hydrogen. If I set it to 0, I'll have pure CO2. So that's how we'll evaluate state 1 and 2. So state 1 we know is pure hydrogen, and also known are the pressure, temperature, 20 degrees Celsius, and volume, 10 meter cube. So state 1 is completely known. For state 2, we have pure CO2. So therefore, the mass fraction is going to be 0 for hydrogen, which means we have pure CO2. And then the pressure is supplied as 600 kPa, and temperature is 100 degrees Celsius. The volume happens to be 3 meter cube. So state 2 is completely known. For state 3, we have a mixture of hydrogen and CO2. So to find the mass fraction, we recognize that the mass fraction is going to be equals M1 is the mass of hydrogen divided by M1 plus M2 is the total mass. So therefore, this is going to be the mass fraction of hydrogen is going to be as shown over here, or if you move the pointer over. We also know what is the total mass, M1 plus M2. We can write that down. And we do know the final volume because the mixture occupies both the tanks now, volume 1 plus volume 2. But even that is not sufficient for the entire state. We need one more variable, either pressure, temperature, energy. So we go to the process panel, and we notice that the process is set up for this mixing problem because we chose a closed mixing app. State 1 is my beginning A state, and state 2 is my beginning B state, the two subsystems. And then the final state is state 3, which is, as you can see, it's hydrogen plus CO2. It shows up here. We have no heat transfer. We have no boundary work. The system volume doesn't change. So now if you do a calculate, it should solve the energy equation because Q equals 0, W external equals 0. And you can see that Q goes out, W goes out. Therefore, the final energy should be computed from this equation, and posted back in state 3. As you can see, E3 has been posted back here. A calculate will produce all other variables in this problem. So the final pressure is found, final temperature is found, and finally, if we go to the process panel, we should find what is the entropy generation in this problem. Sgen is quite high, 9.11, because of mixing between two dissimilar fluids. A what-if study can be performed quite easily. You can change any variable and register its change and click super calculate, and that's all.